Hello everyone, welcome back to Causality with Boris, broadcast from SobolevSpaces. In this video I talk about outcome models and how to use them for estimating treatment effects. Potential outcome means, separate outcome models for treatment groups, and contrast with treatment models are the three main topics in today's lesson. Make sure you watch until the end to compare the takeaways with your notes. And as always, I've prepared extra material that goes along with this video. Check out the link in the description and the PDF will be sent to your inbox. Ideally, we would find the mean outcome as sample mean in the strata defined by conditioning variables. But this is unrealistic for many real-world observational studies. Stratification requires a large number of observations. And then, within strata, we divide observations among treatment groups. What do we do when there is not enough data? We resort to modeling. And here's our rationale. The adjustment formulas give the average treatment effect. It's simply averaging the means of potential outcomes for alternative treatments across strata. If there is enough data to estimate the mean outcome as a sample mean, we use data. If not, we find the mean outcome using regression analysis. For continuous outcomes, we model the mean outcome as a function of treatment choice and values of the strata variables. For binary outcomes, we model the outcome probability. Next, we feed regression models to data. And then we use the regression coefficients to compute the mean outcome for each treatment and strata variable combination. After that, we average the computed means over all combinations of strata variables in the study population. Some people like modeling for the fact that they can choose the type of regression. It can be linear, nonlinear, splines, anything. But there are two different approaches to modeling the link between treatment and outcome. One approach relies on a single model for all treatment groups. The other requires separate models for each treatment. Let's take a closer look. Typical regression analysis involves one model. It links the mean value of outcome with treatment variable and a set of covariates. Treatment variable represents treatment groups. It could be binary or categorical, taking on multiple values. When we are using one model, we assume that the association between the mean outcome and covariates is the same for all treatment groups. We also assume that the difference between groups is the same for any covariate pattern. Now let's consider the binary treatment case. There are two potential outcomes for each individual unit U. Y0 of U if a unit doesn't get treatment, and Y1 of U if it's treated. Each unit comes with the set of covariates ZU. Some points about fitting this model to data. First, for each unit U, data contain observed outcome YU, treatment assignment XU, and values of covariates ZU. Second, the data do not reveal both potential outcomes for the same unit. And third, Rubin's switch determines when the observed outcome is Y0 and when it is Y1. Algebraically, we say that outcome Y is the sum of two potential outcomes, one multiplied by the observed value of treatment variable and the other by its complement. Now we feed the model to data to find regression coefficients. After that, we use these coefficients to find mean outcomes. In one model approach, the same coefficients are applied to the entire study population, whether units are from treatment group or from the control group, but we do it twice. First time, we are setting treatment variable to 1 and to 0 second time. This way, we find the mean outcomes for all treated and all untreated units from the same population. For continuous outcomes, we use linear models. They come with the assumption that change in treatment is associated with a uniform change in the mean outcome, given a combination of covariates. In practice, though, we can use other models to link dependent and independent variables. Just one more thing. I talk about the regression of the conditional mean outcomes on covariates. This type of regression is called outcome models in causality literature. To distinguish them from treatment models, just remember a simple rule. In the treatment models, treatment is dependent variable. In the outcome models, treatment is independent variable. In the graph you see here, the birth weight is plotted against mother's age by smoking history. The green dots are for non-smoking mothers and the blue dots are for the smokers. We may write a single regression model to link the weight to both smoking and age. But it would mean we assume the effect of age is the same among smokers and among non-smokers. It also means that we assume the difference between smokers and non-smokers is the same for all ages. But you can see here that age is strongly associated with weight. At the same time, older mothers are more likely to be smokers. Looks like we're better off with two regression models. One links the weight to age in smokers, and a separate model does it for the non-smokers. This two-model analysis fits two different regression models to data, one for smokers and one for non-smokers. After that, we find two weights at birth given age and two possible smoking history for each mother. For this, we use two different coefficients for age. Notice that neither regression equation includes smoking. The effect of smoking is there through the age-related coefficients. This graph shows squares. They are the means of potential weights according to age. Blue squares for smokers had they not smoked, and green squares for the non-smokers had they smoked. The dashed lines show marginal means for the weight at birth by smoking when pregnant. They are the average of predicted means in the population of mothers if they all smoked, and then separately in the same population if no one smoked. Let's recap. We fit two outcome models, one for the treatment group and a separate model for the control group. Then we compute potential outcome means for the untreated. This is the mean of y0 of u given the values of covariates zu. After that, we use a separate model to compute the mean of y1 of u. Separate models means we use two sets of regression coefficients for the same covariates z. One set for treatment and the other for control group. But the values of covariates zu are the same. Then we average the conditional means over all patterns of z in the study population. The averaging gives us the marginal mean of the outcome as if everyone was treated, and then separately if no one was treated. The treatment effect is the difference between marginal means E1 and E0. It's dependent on the average of z. We can use the same two-model approach when the outcome is binary. A separate regression model is fitted to data in each treatment group. This avoids the assumption that treatment does not affect the dependency of outcome probability on other factors. After that, the conditional outcome probability is computed for each unit in the study population. And we do it twice for the same values of the covariates. First, using regression coefficients for the treatment group, and the second time for the control group. Finally, we average the computed probabilities over all covariate patterns in the study population. This defines the marginal risk of the outcome as if everyone was treated, and then separately if no one was treated. What's the treatment effect then? The difference between marginal risks. You see, in causal analysis there are two types of regression models: treatment models and outcome models. Both are conceptually linked to stratification. In fact, variables that we might use to determine strata are the same variables that we enter into these models. But the models are different. Treatment models link treatment prevalence to covariates. Outcome models link outcome to treatment and the covariates. We use fitted treatment models to compute the propensity score for each unit in the study population. The score shows how frequently treatment that units received appears in similar units. Propensity scores are then converted to the weights, and the weighted outcomes from each treatment group are used to find marginal means. We use fitted outcome models to compute the conditional mean outcome, again for each unit in the study population. But unlike for the propensity score, we do it twice: the conditional mean if the unit were treated, and then if untreated. After that, these two means are averaged to get the marginal means for the corresponding treatments. So here is the main message. There are two approaches to modeling the mean outcome as a function of treatment. You learned that in one approach we use a single outcome model for all treatment groups. The other approach requires a separate model for each group. Don't miss the key idea of separate regression models. They are here to avoid the assumption that treatment does not affect the relationship between outcome and other factors. Keep on watching.